I'm going to walk you through a bunch of different versions of the power rules so that we can see a general, kind of get a general picture for what's going on. So the first one is, let's say I have a function that is just equal to some constant. So like, for example, an example of this might be f of x is equal to the number 3. So we know that this is a horizontal line at a height value of 3. Now what is it, if we use the formula for f prime, so what is f prime of x when f of x is equal to c? Well, that's still the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And so this right here is going to be the limit as delta x goes to 0 of, now no matter what you plug in here, you always get c out, because the function is f of something is equal to the number c, where c is a real number. Okay, so we could say that. Okay, so no matter what I plug in, I get c out. So my numerator is going to be c minus c, because regardless of whether I plug in x plus a little bit or just x, I'm always going to get a height value of c out. You can think about this like this. If I plug in x, I get c out. If I plug in x plus a little bit, yeah, I still get c out. Okay, in fact, no matter what I plug in, I always get c out. So those two guys become c, and this is over delta x, and this is going to be the limit as delta x approaches 0 of 0 over delta x. Now, delta x is never 0. Okay, so since delta x is never 0, and we have 0 divided by a number that's never 0, this inside guy is just 0. Okay, because delta x is never 0. Now, as delta x goes to 0 of a constant, that's equal to just that constant. So f prime of x is equal to 0. So this tells you if you have a function that's the constant function, its derivative is 0, regardless of the x value that you're at. Okay, now let's go up a power. So we're talking about polynomials. I guess I should write that up top here. Okay, now the next one. What if f of x is equal to ax plus b, which would be a linear function? Well, again, f prime of x would be equal to the limit as delta x goes to 0 of f at x plus delta x minus f at x over delta x. And so this right here, using this function, will be equal to the limit as delta x goes to 0 of the following. It's going to be a times x plus delta x plus b minus this guy right here. Okay, so minus this, so minus ax minus b all over delta x. And so that will be equal to the limit as delta x goes to 0 of ax plus a delta x plus b minus ax minus b all over delta x. And that'll be equal to the limit as delta x goes to 0. This guy and this guy are going to cancel. This guy and this guy are going to cancel. So we're left with a times delta x over delta x. Now remember, delta x is never 0. It just gets really close to it. So this, we can cancel these guys out, no problem there. And a again is a constant, it is our slope. So this is equal to a. So f prime of x is the slope. And that makes sense. The rate of change, the derivative. The slope of this line is, oh, look at that, it is the slope. Okay, so those are the two easy ones. Now let's get a little bit harder. Let's see how much time we've used. 5 minutes, we're doing good. So let's say we have some f of x that's no longer linear, but it is a quadratic, okay, or a second degree polynomial. Well, if that's the case, then to find f prime, we'll take the limit as delta x goes to 0 of f at x plus delta x minus f at x over delta x. So we got to take this guy and plug into here. So we get the following: a times x plus delta x squared plus b times x plus delta x plus c. This is this guy right here. And then f of x is just this guy, so we got to subtract f of x off. Remember to distribute your negative. Okay, and now we've got to FOIL this. Don't just distribute that square. So this is a times the quantity x squared plus 2x delta x plus delta x squared plus bx plus b times delta x plus c minus ax squared minus bx minus c all over delta x. Okay, so let's just do one more long step out here before I start canceling things. So this is going to be ax squared plus 2ax delta x plus a times delta x squared, again bx plus b times delta x plus c minus ax squared minus bx minus c all over delta x. Now what cancels? Well, the ax squared and the negative ax squared, the bx and the negative bx, and the positive c and the negative c. So what's left over? Well, this is equal to the limit as delta x goes to 0 of 2ax times delta x plus a times delta x squared plus b times delta x all over delta x. We're going to rewrite that as this: delta x times the quantity 2ax plus a delta x plus b all over delta x. So these guys are gone now, and the reason we can cancel those is because, one, delta x is not equal to 0, and we're substituting in a new equation that represents the old equation for all values except for when delta x is 0, and we know that it's never equal to 0. So we get this, and now when we take the limit of each of these pieces as delta x goes to 0, this guy goes to 0, so this whole guy right here cancels out, drops out because it's 0. So we're left with 2ax plus b. Okay. Now what did that give us? Well, that told us that if we take this power, drop it down, and multiply it, take this power, drop it down, multiply it, and subtract 1 from the power, we end up getting this value. And I'll make that more clear at the end of this video. or in the next video, depending on if I can't get this one to load due to time. So in general, we can take the derivative of each separate piece of a polynomial by itself. So here's what I mean. Let's say we had f of x being equal to ax squared plus bx plus c. We can take the derivative of each of these pieces. The derivative of this first guy is 2ax. The derivative of the second guy is b, and the derivative of this third guy is 0. And those, ladies and gentlemen, come from up here. Okay, if you look at these derivatives. So, what is our general rule? Well, we could keep going. I could do another example. I could say, well, what is f of x where it's ax to the n? And the derivative of that is equal to n times a times x to the n minus 1. Here's how it works. You take the power and you drop it down up front for multiplication, and then you subtract 1 off the power. So let me give you an example. Let's say we had g of x equal to 12x to the third minus 16x to the first plus 7. Well, then g prime is 3 times 12 x to the 3 minus 1 minus 16 times 1 times x to the 0 plus, now there's nothing here, right? This is a constant. We know the derivative of a constant is 0. So this would be equal to 36x squared minus 16, because x to the 0 is 1. So this guy is equal to 1, so minus 16. So this power rule is a lot more efficient, or it's a lot quicker than doing out the derivative by hand each time. Okay. So let me give you the general rule, like they have in the text, is this guy right here. Now to prove this rule, okay, we'd have to use the binomial theorem. And there's a nice, your text, there's a nice little proof for it. I'm not going to do it here. But anyway, if you want to take a look at it, it's not a bad idea to take a look at it. If I was going to do an extra credit, maybe that would be one of the questions, is prove that this is true using the binomial theorem. Again, it's proven in your book. You'd have to go through and make sure you know all the steps. But the thing that you want to get out of this is that if you have a polynomial, so I'll give you one more. Let's say we have h of x, and that's equal to 3x to the fourth minus 7x to the third plus 4x squared minus 6x plus 10. Then the derivative of that is equal to 4 times 3, which is 12, x to the third, because I subtract 1 off the power. 3 times 7 is 21, x squared, subtract 1 off the power. 2 times 4 is 8, x to the first minus 6 plus 0. So this is the derivative. Now again, you can do it out the long way, but here is now your power rule for doing the short way.